Okay, so my name is Paul Rosenbloom. I'm a professor at the University of Southern California. I work in computer science there as well as the Institute for Creative Technologies. I've been interested in artificial intelligence since at least the, 1970s. And I've always been interested in the question of how do we understand intelligence, how do we model intelligence, and in particular, how do we get all the pieces together so that we can build something that approximates human-level intelligence. I started working on that in graduate school back in the, when did I start graduate school? I guess it was the mid to late 70s. I went to Carnegie Mellon University for a Ph.D. to work with Alan Newell, who's kind of the father of cognitive architectures. And I really wanted to work with him on those kinds of ideas. So it's been a long process. I've been working on this kind of thing for a long time, though it did take 10 years to do other kinds of things, and then got back into it 5 years ago. Well, I started it before the AI winter. And the AI winter was really kind of overselling of the commercial aspects of expert systems in particular is what caused it. It had really nothing to do with my interests, which were in understanding intelligence and how to model intelligence. Some of the stuff that we did early on spun off and was part of the expert systems boom. So in the early days, we were working on production system architectures for cognition, and that was certainly the basis for a fair amount of the expert systems boom. But the fact that there was lack of commercial interest after that didn't matter that much because the core scientific issues were still there. Part of intelligence is having lots of knowledge and using it effectively. And the expert systems boom came about because of the first availability of techniques that were capable of handling reasonable amounts of knowledge, reasoning about it, and doing that reasonably effectively. So you could start encoding human expertise into computer systems and getting them to make kinds of decisions that you couldn't do with other kinds of technologies. So AI kind of produced that capability through the development of both the kind of forward chaining rule systems at Carnegie Mellon and the backward chaining kinds of things that were developed at Stanford. Those were kind of the seeds for the expert systems boom, though other kinds of AI techniques became part of as well, frame-based systems and a few other kinds of things. So it was really the first spin-off of useful technology from the beginnings of our understanding of intelligence. But it had its limits, and it ended up being oversold, and as these things often are. You still see that kind of technology used, but it's not the pervasive panacea that some people had thought it was going to be. And that's what led to the first AI winter. There's certainly been other spin-offs from AI in terms of useful technology since then, but they've often been other kinds of things, planning technologies, machine learning, vision, speech, things like that. So it depends on what you mean by those, but the classical paradigm in AI, I wouldn't call Boolean, but symbolic. So the notion is that you have symbols that represent things, and you have structures and expressions of those symbols that are manipulate, and through that you do various kinds of high-level reasoning. The early days in AI were focused on problems like search and problem solving. How do you take a complex problem like chess or finding a path in a road network, and how do you search for solutions to problems cast in this kind of combinatoric way where you can apply a sequence of actions to solve a problem, but the trick is to figure out what's the right sequence of actions to reach your goals. So that was much of the early part of AI focused on that kind of thing. And then on what's called knowledge representation and reasoning, often in the early days via logic of one sort or another, often what's called first-order logic, where you have variables and quantifiers and things like that. So there the focus was on representation of knowledge and how do you reason with the knowledge. So through its early history, AI was focused on these kinds of issues of problem solving and knowledge. And again, it kind of reached certain limits with those kinds of technologies. The revolution that we saw coming after that was one based on understanding how to do probabilistic reasoning in a tractable fashion. So this is where you can deal with uncertainty. I don't know definitely that it's this, but it might be this or this or this, and I think it's more likely to be this. You can assign numbers and distributions over that, and that lets you deal with a variety of other things. That in combination with large amount of data, which the internet and the web have made available, have kind of changed the paradigm in the field for many years to where it became much more statistically oriented. It de-emphasized the symbolic things. It still had aspects of it, but it was much more simple. And areas like machine learning and even the other parts of AI got much more statistical and much less kind of intensive reasoning. What we're seeing now, I think, actually is the point where you're taking that about as far as it can go. And what people are trying to do is combine those paradigms. So the original, what we learned about symbolic processing with what's been learned about probabilistic and statistical reasoning, and see if we can get the best of both of those worlds. And that's actually where the work I'm doing in architectures these days is focused. My original work, I worked on something called the SOAR architecture for about 15 years, from the early 80s to late 90s. It was really done jointly with John Laird and Alan Newell. Alan was John and my advisor, and then we kind of formed this joint project after we both finished our theses. John still works at that at the University of Michigan, so SOAR has been under development for 30 years, primarily in the symbolic paradigm, but with more and more bits of other kinds of things as well. When I got back into looking at cognitive architectures about 5 years ago, my goal was to kind of blend the 30 years of understanding of cognitive architectures from SOAR and ACT-R and other things like that with the 30 years we've had of understanding what are called graphical models, which have sort of come out of the probabilistic reasoning world, and see if there was a new basis for building integrated artificial general intelligence, whatever you want to call it, based on that kind of a combination. And so that's what I've been looking at over the past few years. So I found actually that intro to AI course kind of odd because it was almost completely probabilistic and they mostly ignored all the other stuff. But that's very much Sebastians' paradigm. Peter comes from the symbolic world, but still that was a very small percentage of the course. Yeah. Turns out both my wife, who's a physician, and my son, who was an undergrad at Stanford at the time, took that course. So I followed it quite closely and helped them out in various ways to help them to understand it, because they were teaching things actually in that intro course that I didn't understand all that well. Some of the things like particle filtering I'm still learning about, and I was very surprised they would teach them in an introduction to AI, but that's Sebastian's approach. I guess my bet for the future is on this combination of the probabilistic and the symbolic, and that's the path for the future. I think machine learning has a lot to do with that, but it's not all machine learning. There are other aspects of structure that we need to understand in order to build a complete cognitive system. You can't just assume what's called a tabula rasa, a blank slate, and then expect learning to fill everything else in. We clearly learn a lot as humans, but we start with a huge amount of structure. And the notion behind a cognitive architecture is it's the fixed structure that you start with, on top of which you can learn knowledge and skills and other kinds of things to adapt yourself to the environments that you're in. But you need to understand what that fixed structure is to begin with. And it's not just a learning mechanism. And in AGI, you see a range of hypotheses. You see some which really focus on a pure learning mechanism. So universal artificial intelligence and AXCR, the assumption is all you need is one general learning mechanism, and that's a simple, elegant way of casting the problem, but it turns out not to do the job in practice. You can go to the other extreme and get very complex systems with many different components, and then you have to figure out how to really leverage that combination. My own approach is closer to the universal artificial intelligence, but not all the way there. It's, as I call it, cognitive Newton's laws. You're looking for a small set of general principles through whose interactions you get the diversity of intelligent behavior. So I'm more at the uniform or simple end, but not to the extreme of saying it's all just one thing. It's for me, I'm looking for a small set of things that interact generally. Well, so the SOAR architecture is what I worked on from the early 80s till the late 90s. That was the previous one, so I worked on that for about 15 years. That was a purely symbolic architecture at the time. And then I went off and did other things for about a decade and then got back into cognitive architectures and started developing Sigma. Though it only got a name recently because I was ambivalent for a fair amount of time as to whether I was building an environment in which to investigate cognitive architectures or whether I was building a specific cognitive architecture. And I finally concluded I was actually building one. So that's when I gave it a name. I decided that essentially so I'm building Sigma on the basis of what are called graphical models. They're a general way of decomposing complex problems into products of simpler problems, mapping them onto graphs, and then solving them in fairly efficient ways. What's interesting about them is that they provide state-of-the-art algorithms across many different parts of what's necessary for general intelligence. And because they provide a number of different algorithms and different variations on those algorithms, there was the possibility that you could provide an environment in which you could try many different variations on architectures. But what I found is I tried to leverage that to get the full set of capabilities I wanted, that they still constrained each other to such an extent that I was kind of designing one system rather than a space of possible things. And so it was really the constraint that comes when you do integration that led me to realize I was really focusing on one working thing, and that though I could provide some space of variation, those variations were really constricted by the necessity of getting these things to work together in the way I thought they ought to. There's nothing confidential in Sigma. It's all the software is open source and it's all published publicly. I'm developing it at the Institute for Creative Technologies, where their focus is on combining computing technology and entertainment expertise for doing education and training and other kinds of things. A big part of what they do is build virtual humans for these kinds of environments, and a big focus is on the social aspect of virtual human interaction. So what we're pointing to on the more applied side is, in say the next year or so, is the development of a virtual human with sort of Sigma as its brain. That's what we're pointing to on the more applied side. It hasn't made it out commercial or anything like that. It's still very much a research product. Well, there are a variety of things. Some just have to do with software engineering. Some have to do with documentation. Some have to do with efficiency. Some have to do with functionality. So we're still trying to understand the range of functionality that are required to be there and how to implement them in Sigma. We're trying to understand how to get it so that we can build kind of real-time virtual humans. I think the first virtual human we build will be slower than real-time. And that's not going to be very interesting to anyone in an applied setting. So there are a lot of efficiency issues when you're doing AGIs. And we suffer from those, though there's real potential to get there, but we're not there yet. It's research code. It's in a language called Lisp. We don't have a user manual. We don't have tutorials. We don't have really a support team for it. So there are lots of issues in sort of getting to the point where it's out there and available and easy for people to use for what they want to do and all of those kinds of things. So it's still a few years off before that's going to happen. But we hope to have something a little more real than what we've been doing so far with the kind of toy investigations. What I've really been pushing in Sigma so far is breadth of capability. And I haven't tried to go real deep in any of the capabilities, but because the big focus here is the integration across many different aspects of cognition, including perception and motor control, we're trying to hit high points kind of all across that spectrum so we can, as quickly as possible, find out what it can do, what its limitations are, how do we fit those various things together. And so it's a thin veneer rather than it's highly capable in any one particular area. So that's part of the issue also. We haven't run into any major limitations yet. All of the things that I thought we ought to be able to do in Sigma, we're finding ways of doing. And we're finding ways of doing things that I hadn't necessarily anticipated we'd been able to do. So I don't yet see what that boundary is going to be. I know we can go a lot farther than we did in the old versions of SOAR. I stopped working on SOAR partly because I couldn't see how to make the kind of progress anymore I wanted to make. And I got back into Sigma because all of a sudden I could see, oh, all these problems I didn't know how to solve in SOAR, I think I can see how Sigma can do them. And so I'm still kind of exploring to the extent to which that's true. And so far I haven't found anything that I think is important for general intelligence that isn't going to fit. There certainly could arrive. They could arise at any time, but so far they haven't. So maybe I'm an optimist, but I don't see that much difference between the optimistic view and the realistic view. I think we'll get to the point where we can incorporate kind of all of the aspects of intelligence that we as a field understand. I think I'll be able to incorporate all of that and integrate it together within Sigma. So that's really the optimistic view, and we'll understand how to get them all to work and to get them. The hard approach is probably going to figure out how to get them all to work together. Though Sigma provides some aid in doing that, and I think that's fairly realistic. Again, I don't see the limitations out there that are going to hold it back, and I've seen those in other systems and other approaches, and I've understood well why it's being held back. So far, I don't see that, but there's always the things we don't understand yet, and any of those could be showstoppers. But so that's kind of, I think, where we're going to end up. When I'm pessimistic about it, what worries me most is simply the question of efficiency. Whether we're going to be able to build these systems that run in real time on the complex problems that we want to be able to ultimately solve. Now, I'm taking what's called a uniform approach in Sigma. I'm trying to do everything as much as possible, kind of in the same fashion across all of intelligence. Now, it may be that I'll be able to do everything in a uniform fashion, but it may be that I won't be able to do everything efficiently in a uniform fashion. If that's the case, it's possible Sigma will fail, or it's possible I'll have to do special purpose optimizations under it. I don't know what's going to happen there, and that's the thing actually that worries me the most at this point, is whether as we grow the system in capabilities, as we grow the system in knowledge and skills, and the size of the tasks we want to tackle, whether we're going to be getting anywhere near the level of efficiency we're going to need for them. It's possible. You talked about DWave. Is that what you said?
Anyone.
Right. So there actually is a DWave computer at USC. And I've talked with Jordy. I forgot his last name. Was the head
Jordy
of
Rose.
Jordy Rose, right. Actually, I met him at the last at Humanity Plus at Caltech. And there are actually interesting relationships between the kinds of problems the DWave computer solves and what's necessary for graphical models. The kinds of things they do right now aren't quite flexible enough, but there are possibilities for the future. There are many possibilities for efficiency. There's different kinds of optimizations, there's parallelization, there's the future potential of quantum computers. Any of those might help. So I say it's when I'm being pessimistic that I am afraid that we won't keep up, but because that's my biggest worry. The rest of the stuff, I see paths at this point, and I don't yet see the showstoppers. I believe it will, in one form or another, whether any of the existing ideas or what does it. But the grand challenge of building human-level intelligence, general intelligence, in computers, I do believe we'll solve, and when we solve it, it will have a huge impact on the world. I'm hesitant to predict when or by what technique we'll solve it. We all lay our bets on those things, but if we can do that, it does change the world. Society is never really ready for technological breakthroughs. It may think it is, and then it always discovers the implications of them are different from what it anticipated. So no matter how much it anticipates and how much it tries to prepare, it never really understands what's going to happen. So people have started to think about it. People are starting to think about the ethics and what happens to people and all the other aspects of it. But again, I don't think we are good at anticipating what the implications are. So no, we're not ready. But we never are. Well, there's an interesting question as to whether are people as far as you can go in general intelligence. What we don't know is Essentially, can it be better? We know that it's possible to get better, to be better, much better than people at very narrow things. What we don't know is whether it's possibly better at general intelligence. So if it is, then it's possible we'll build things that are smarter than people. And we know there are some people smarter than other people, so maybe we can at least build these so that they're the smartest people. But yeah, I think it's really an open scientific question as to whether there's much headroom above human intelligence, that we can actually build systems that are that much smarter than people. I don't really have any confidence that there is. If you look at some of the analysis, so John Anderson, who's a psychologist who did ACT-R, kind of the main cognitive architecture on the psychology side, he focused or developed this concept called rational analysis, where he did a lot of work trying to show that the people are irrational if you look at them in the narrow. If you look at the big problem they're solving, they're actually pretty rational. Now, I think he's backed off on that to some extent, but the basic notion that we are actually fairly close to optimal in the environments in which we operate would tend to imply that you can't be all that much better. Now, there are a lot of qualifications on that, but as I said, I think it's very much an open question, how much room there is above what people can do in terms of general intelligence. And if we can build very special purpose intelligences that aren't general, people can use them as tools just as machines can use them as tools. So all of that kind of thing is possible. And we certainly will generate very powerful, specialized intelligent capabilities. Well, we already do that now. I mean, computers and calculators and phones, they all augment us in all sorts of ways. Brain-computer interfaces, to the extent that they will be possible and sustainable and all of that, will bring it to a whole new level. There's a lot more we need to understand about how the brain and how to communicate with the brain and so on. But there's no question that technology can augment our intelligence in various ways. A lot depends on how close a connection you can have between them. A lot depends on how you divide the problem up between the person and the automated system. But all the computer tech tools we have are essentially augmentations of our intelligence in one sort or another. Brain size in humans and intelligence doesn't correlate, as far as I know. But you'd have to think there's more potential if you've got a larger brain and more cells for whatever it's going to do. But so again, we don't know if there are different kinds of intelligence, or whether, if you're looking at general intelligence, whether it all narrows in on essentially one path with maybe small variations, and other things are missing pieces of it or approximations to it in one way. That's just something we don't understand, because we don't understand the space of intelligence. Psychologists focus very much on people and some on animals. AI people have the freedom to look at wider varieties, but we're not close to general intelligence there yet, so we don't know whether there's that big a space of possibilities. Will alien intelligence be different than ours? Again, if I were going to lay my bets, I would say probably not that different. Sensory systems can be quite different, but the core of intelligence, in terms of responding appropriately given goals and what you know about the world and your perceptual capabilities, that essence of intelligence seems to have to be there. Differences at the margins, but the core of it, I think, somehow has to be the same. And again, so it's hard for me to understand how something can be much more intelligent unless something can be faster, but it's not going to be exponentially faster unless it's perhaps quantum. And even then it's not clear. But it can be somewhat faster and therefore somewhat more intelligence, like there is a range in people. But I wouldn't lay odds that there's a possibility for very radically different intelligence or very radically higher intelligence than what we've seen. It's possible. I stay open to the possibility. I just don't think it's likely. So most of those have to do with what's required long-term for survival in particular environments. And certainly if you're in a different environment, your goals can be different. It doesn't necessarily mean a different kind of intelligence, but it may mean that you have different drives, because it's whatever's required to survive in that kind of environment. So that's well within the space of a variation that we could expect to see in intelligence systems.